So, good evening. In our last class, we have been discussing about the filter designing aspects. Right? Now, let's look into the filter design by placement of poles and zeros. Okay. So, before we go into that, let us look into the Laplace domain. Suppose there are 2 points Z and P. Okay. So, the vector is given by the vector z and p. The distance between this one is given by this p minus z vector, right? So this is the vector. So there would be two vectors, origin to z, that would be the z vector, and origin to p, capital P, that would be the p vector. And among these 2 points, we will be having this p minus z vector. Okay. Then when we place poles and zeros on the S plane. So we'll be having some certain vectors to the point P. Okay. So these poles to the point P, they are usually regarded as D1, D2. So let's assume that we'll be naming them as D1, D2. And the distance between the vectors, not the distance, the vectors between the zeros and the point P, they would be regarded as R1, R2 like this. Okay. Now, when we talk about the filter designing, so what happens is that this point P, it is on the imaginary axis. Okay. So this point P, it varies on the imaginary axis. Okay. So if you look into the transfer function, so what we will be having? We will be having Hs equal to Ps by Qs, B of n, where B of n, it is called the scaling factor. Okay, it is regarded as the scaling factor. And then we will be having the polynomials s minus z1 multiplied by s minus z2 multiplied by s minus zn. And similarly, at the denominator also we will be having the similar thing. Okay. Now, we know that this S plane is basically, we are talking about the P point which will be varying on the imaginary axis. So if we replace S equals to P, then we get P minus Z1. So where P is the point on the S plane. P is a point on the S plane. Okay. So our this equation, it transforms into this equation, right? Now again, if you see, these are all vectors, right? So in the next slide, if I go, so if you see over here, what we have Bn into R1 into e to the power j phi 1. What is phi 1? Phi 1 is basically the angle between the x-axis and the vector point connecting the zeros and the point P. Okay, like this. So we go in the anti-clockwise manner. We go in the anti-clockwise manner everywhere. Okay. So that angle is regarded as the phi 1 in the case of zeros and theta in the case of poles. So theta 1, theta 2, like that we'll be having for the poles. For the zeros, we'll be having phi 1, phi 2 and so on. Okay. And the distance, it is regarded as R1, R2 for the zeros and D1, D2 for the poles. So if you see, we can rewrite the same equation in this format: R1 into e to the power j phi 1, R2 into e to the power j phi 2, and so on, divided by D1 into e to the power theta 1 multiplied by D2 e to the power theta 2, and so on. Okay. So what happens is that Bn, over here it becomes Bn equals to R1 R2 Rn, okay, divided by D1 D2 Dn multiplied by e to the power j phi 1 plus phi 2 plus up to phi n minus of theta 1 plus theta 2 dot 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 to theta n. So what does this mean? What are these? These are nothing but the product of the distances of zeros to P, to the point P, right? And at the denominator we will be having product of the distance of the poles to the point P. So this is the real part, this factor is the real part. So what is this? This is nothing but the modulus of h of s at the point P. At the point P. Okay. Similarly, for the phase, what we are having, this imaginary point, it is the phase. So it is basically the sum of zero angles to P minus sum of pole angles to P. Okay. But P is not a fixed point. So from this equation, we will be getting one plot which is modulus of h of s. Now P is a varying point on the omega axis, so we will be getting some plot over here. Okay, say for example like this or whatever. We'll be getting some plot. Okay, so if it is a filter, it may be a high pass filter, it may be a low pass filter. If it is a low pass filter, we'll be having something like this. Okay, sorry, no, we are talking in the analog domain, so this omega will be this capital omega. So we'll be having the low pass filter like this. If you want to design a high pass filter, the high pass filter should be like this. Okay. So combining these two, we can have band reject filter and so on. Okay. On the other hand, if we plot the phase with respect to omega, okay, so that will be our phase response. Okay, because P is varying over this frequency axis in both the cases. So we'll be getting the amplitude response and we'll be getting the phase response. So what is the takeaway from here? The takeaway is that if at a particular frequency, if we know the location of the pole and if we just find out the distance between the poles and the poles and the frequency and the zeros and that particular frequency, then we should be able to determine the amplitude response. Similarly, if we can find out the angles between the x-axis and x-axis means parallel to the x-axis and the direction of the this or the this direction of the vector, then that would give us the phase response. Okay, so by summing all those angles to the point to that particular frequency point and summing subtracting it subtracting the sum of the pole angles to the point P, we can also get the phase response. Okay, so this is the key idea. Now what happens over here, मैंने ये अपडेट करके नहीं भेजा था, it might not be the updated one anyway, आज छोड़ दो. So what happens over here? Okay, in this plot if you see, we are having a single pole filter. Okay, and we are assuming that 0 is present somewhere in the z plane which is far off from this pole. Okay, so what we have, if you see, this is the pole and poles and zeros, they always exist as conjugates. Okay, they always exist as conjugates. Okay, so both in the Laplace domain and in the z plane. Okay, so hence if you see, they are present as the conjugate. Okay, now if you look over here, what is happening? Our this frequency, it is changing, analog frequency. So from this pole to 0, we are having some amplitude. Okay, so how it will vary? So we know the Hs, it is directly proportional to the 1 by the pole distance. Okay, 1 by the pole distance. So when our point P it is at 0, so we'll be having 1 by d, so it will be having a definitive amplitude like this. Okay, so we will get a particular amplitude. Then if we come to this point j omega, it will be somewhere over here. Why it is somewhere over here? Because the distance d, it is reduced. So if the d is reduced, this whole factor will be increasing. So it has increased like this. Up to what point it will be increasing? It will be increasing up to the j omega point, which is the critical point, okay, which is the critical point over here, okay, and at this point the distance will be minimal, and since the distance will be minimal, our amplitude will be the maximum, okay. And what this frequency is called, what this frequency is called, this frequency is called the resonance frequency of the filter, okay. At the resonance frequency, the pole will be having either the maximum gain or the minimum gain, okay, maximum gain or the minimum gain. You must have studied about this resonance frequency in the RLC circuits, right? So the same principle, either the resonance may increase the power or it may decrease the power. You're getting my point? So in this case, by applying the pole, it is increasing, and that highest point, it is called the resonance frequency. And thereafter, as this point move towards the infinity, what is happening? What is happening to the D? It is increasing. So what will happen to the HS? See, it is decreasing. Okay. So what kind of filter it is? It is allowing the low component frequencies to pass through, and at high frequencies, it is coming down to zero. So it is a low pass filter. Okay. Similarly, if you measure the angle, you will find the angle varies between 0 and -5. Okay. So in this reverse sigmoidal curve phase, you will be getting this point. Now, what about this conjugate pole? Because it is also present over here. Okay. So, basically what happens, our h of s, it is directly proportional to 1 by d dash. But in most of the cases, what happens, this, the distance of this pole to the frequency axis, it is quite high. It is quite high as compared to the distance d. So the effect of this d dash, it is taken to be negligible, and hence it is not considered while we are trying to decipher the information about the this what you call uh, this amplitude response, okay, or the phase response. Okay. Similarly, in the next stage, in the next this row, if you see, we are having a zero. Okay. Now we discussed that number of poles should be always greater than or equal to zeros. Okay. So in this case, what is happening? We are only having zeros. So we are considering that the pole is present somewhere at the infinity. Okay. So again, if you apply the same analogy, what is happening? In this case, Hs is directly proportional to the R. So if you see, the R is having a definite distance over here. So we start with a definite distance over here, amplitude, and then we, as we come to the resonance frequency, it becomes the minimal, and again this R increases. So again we can say that there is an increase in the amplitude response, and in this case, at higher frequencies, as the gain is increasing, so it is a high pass filter. Okay, and here you have the corresponding phase response. So just by placing a pole and by placing a zero near to a what you call frequency axis, you have successfully designed a low pass filter and a high pass filter. It is as easy as that. Now, to understand how the placement of the pole, it would affect the filter response. Okay, so what we need to do, we need to have an understanding about the S-plane. So in this regard, we have a concept which is regarded as the rubber membrane concept. It is regarded as the rubber membrane concept. Okay, so what it says is that, suppose this is my S-plane. Okay, and on this S-plane, I have attached one rubber membrane. Okay, balloon देखा ही होगा आपने, right? So in the balloon, if someone stretches, if you remember correctly, if someone just pricks his finger from beneath, what will happen? It will form a cone like structure. First balloon, it is a rubber membrane basically. So you are having a plane, and then when you are putting your finger from the beneath, you are getting a cone like structure. Now this rubber membrane concept, it is telling the same thing. On the other hand, if you push the balloon from the top, what it will do? It will bring the balloon surface downwards. So when you are putting the finger, that means you can just consider that as a pole. Okay, so you are putting the pole is increasing the gain, and when you are pressing the rubber membrane, it is acting as a zero. Okay, so if I place a pole over here, if you remember, as I told you, you are getting a cone, and when you are getting a cone, so what is happening over here? If you look at this pole location, and if it is near to the j omega axis, why I am saying it is nearer to the j omega axis? Because we are only interested on the frequency plane. Okay, we are only interested what is happening on the frequency axis when we are placing the pole or the zero. We are not at all interested on what is happening away from the frequency axis. Okay, we are only interested in the frequency axis, because when we talk about the filter response, our response, what we plot basically, in either of the case, whether it is a phase response or the amplitude of the response, in both the cases, our independent axis is the frequency. Okay, our independent axis is the frequency. You're getting my point? So we are basically interested in the frequency, on the frequency axis, and nowhere else. So when we place this pole, we have a cone and it is having a base. Now if I cut this cone over here, so what is happening? So it is a cone, say for example like this. So see, over here it is the cone, right? Now if I'm cutting like this, say this is the frequency axis. So at this point, we are having some amplitude, right? We are having some amplitude. Now this amplitude is the gain of the filter at that particular frequency. Okay. So as you go from one frequency point to another frequency point, you will be getting something like this, right? So as you are changing the frequency, at zero frequency it will be having some gain. As you go to the other frequency component, next frequency component, you will be having another thing. So in this way you will be getting a point like this. Okay. So this will be your amplitude response. Okay. This will be your amplitude response. And rubber membrane concept, please be reminded, as I told you, it is a qualitative method. It only gives us an estimation on the amplitude response. It does not give you estimation on the phase response. Okay. So what happens if I take this pole and if I move it towards the frequency axis? So if I move, suppose this is the frequency axis, as I told you, and if I moving this towards this thing, what is happening? So this higher portion, it will come over here, they will shift. So what is happening? Gain at that particular frequency, it will increase, right? And if you take this pole and if you push it away from the axis, what will happen? Gain is decreasing. Okay. So placing a pole nearer to the frequency axis increases the gain of the filter. If you take that same pole, you are just changing the alpha value, and alpha value means the real value, without changing the j omega value. You are moving the pole away from the frequency axis, and the frequency response will come down at the j omega axis. Okay. So also in the other points also, but the main effect will be on the j omega axis. Okay. So if you consider the placement of the zero in this way, so we can say that zero can be placed anywhere on the x-axis, anywhere on the s-plane, right? So if you place the pole, if you place the zero on the j omega axis, it is making the filter amplitude zero at that particular point, and we will be having no frequency component. So we are basically stopping that. Okay, and when we move away this 0 point away from this frequency axis, what we get slowly, we'll be getting that the amplitude is increasing. So we are having this kind of thing. So suppose this, over here you are having this frequency axis. So what is happening if I am moving like this? So what is happening in this axis? It is increasing, right? Similarly, if I move the zeros in this way, what is happening? It is again increasing. Right? On the other hand, if you consider the pole this way, if you consider, so if I am placing it on the nearer to sorry nearer to the axis, if you see the amplitude is high, and as I move it, what is happening? The amplitude is reducing. Okay, so in this way we can have an understanding that how the placement of the pole and the zero, they are it is affecting our frequency response. Okay, so we have seen that just by placing a pole nearer to the zero, what we are doing, we are creating a low pass filter. Okay, we are creating a low pass filter because negative frequency we need to avoid. Okay, we will not consider that. So if you see from 0 to omega, it is allowing, and thereafter no frequencies are being passed, so it is a low pass filter. Now if you have to design a high pass filter, what you have to do, you have to place poles at higher frequency. Okay, so that will help you in designing a high pass filter, or you can also use the zeros in a specific way, as in this case, so that you can get a high pass filter response. Okay, are you getting my point? So then we have the band pass filter. Band pass filter, it is basically a combination of a low pass filter and a high pass filter. So over here, this is your omega L of the low pass filter. Okay, and this is the omega L of the high pass filter. If you consider for the consider this for the composite band pass filter, basically this is your omega L, and this is your omega H. Okay, but this is for the omega L of the low pass filter, let me say, or omega C for low pass filter. Let me give the nomenclature in this way, and omega C for high pass filter. Okay, so for the band pass filter, this is our omega L and omega H. Are you getting my point? So by combining this one low pass filter and a high pass filter, I can get the band pass filter. But the condition is that the omega C LPF, it should be greater than the omega C high pass filter. In the case of if you are designing a band pass filter. Okay. Similarly, if you have this band reject or band stop filter, what you will be having something like this. So here you are having omega cutoff LPF, and here we will be having omega cutoff HPF. Are you getting my point? So next, what we have for the band reject filter, this is the omega L, and this would be your omega H, right? So in this case, what is happening for band stop filter? Your omega C HPF, it should be greater than omega C LPF. So by combining low pass and band pass filter, I can either design band pass filter or band reject filter, but you have to remember the conditions. Okay. And lastly, we can have the notch filter, which is a limiting case of band reject filter. In the, you can go and wash your face. So, so it is a limiting case of the band reject filter or the band stop filter. Okay. So where only a single frequency is being stopped. Okay. Any doubt till now? No? Okay. So using the low pass filter and the high pass filter, how can I design the band pass filter and the band reject filter? So while we are designing the band pass filter, we have seen the condition. What are the condition? So over here, what we have is that we will be first passing the signal through the LPF, low pass filter. So if you see, this whole section will be passed. Then this will be passed through the high pass filter. So high pass filter is this portion, but the external portion, this white portion, is already rejected. So what we are left with? We are only left with this portion. So just by putting this thing in the sequential manner, so low pass filter followed by a high pass filter, we were able to design a band pass filter. Okay, we were able to design a band pass filter. Okay. Now, if you change the positions, will it affect? No. The reason being, then in that case, we'll be having this high pass filter area first, and then we'll be having this low pass area first. So initially the low pass components will be rejected, and in the second stage the high pass components will be rejected, and we'll be getting the same intersection area. Okay. On the other hand, if it does not meet the criteria what I said in the previous slide, so what will happen? The low pass filter, it will be like this. It has already rejected the high pass filter components. So what will happen? It will be rejected. So when you apply this low pass filter also, these are already rejected. Similarly over here also, what is happening if you apply this? If you apply this high pass filter, this is selected, and when you apply, there are no frequency band is available. Okay. Here, first we are applying the low pass filter. These are selected, and when we apply the frequency HPF, there are no frequency components available in the high pass region. So this is also rejected. This is also rejected. Right? Similarly, over here also, this is also rejected. This is also rejected. So we will have nothing. Okay. But so having that understanding or this principle that frequency LPF should be cutoff frequency of the LPF should be greater than the cutoff frequency of the HPF. It is of paramount importance. Okay. On the other hand, when you have the band reject filter, if you see we are having two separate combinations, and we are as if we are adding from the low pass filter we have just rejected this band, and from this high pass filter we have just rejected this band. Okay. So what we need to do, we need to combine these two. So what we will be doing, we will be taking the signal output from the low pass filter, we will be taking the signal output from the high pass filter, and then we will just add it, and we will be getting the band pass filter. band pass filter. And band reject filter, it is just a critical case of band stop filter where we are just uh, what do you call it, subtracting or negating only one specific frequency. Okay, clear? So you should keep this figure in mind. So what is happening? So what thing? What you get? Tan inverse of b by a, tan inverse of b by a plus pi over here, tan inverse of b by a minus pi, and tan inverse of b by a. Fourth quadrant, and at the positive real axis what is happening, your phase value is 0 when you are in at this position, when 0 plus bi at this position it is pi by 2, at this position it is minus pi, and at this position it is minus pi by 2. This is the basic thing from your class 11 12. So I hope you remember. Okay, yes or no? Okay, good. So coming over here, so in this case, we have already discussed about this parameter where we have looked into the mapping of the system. Okay, we have also discussed that while discussing analog frequency, we will be discussing about this capital omega, and for the digital frequency, we will be using the small omega. Okay, so just to recap, we discussed and also discussed that ECG is having frequency component in the range of 0.5 to 100 Hz. Okay, so our sampling frequency should be minimum of 100 Hz, but practically, if you use low cost digitizing systems, you will find that you need at least 10 times of the maximum frequency. Okay, and most of the laboratories, especially in India, you will be having low cost data acquisition system, so you have to be very careful about those. So while acquiring data using your low cost data acquisition system, you should be very careful that whatever is your maximum frequency FM, you should take the sampling frequency which is at least 10 times of your maximum. Okay, so now, if what is happening? Say for example, if it is 1 kilohertz, okay, where should be your this 100 hertz? Where should be your 100 hertz? So it's simple mathematics. So 1000 hertz, it is at 360 degree. Okay, you apply your unitary mathematics. Your 100 hertz will be at 36 degree. It will be somewhere over here. 100 hertz frequency. Did you get it? How did I get it? Our 1000 hertz, which is the sampling frequency, it corresponds to 360 degree, right? So we talked about that we need to have this 100 hertz. So where should be this 100 hertz? So your 1 hertz will be 360 by 1000, and your 100 hertz it should be 360 by 1000 into 100, which is equal to 36 degree. Okay, समझ में आ गया? So what is happening? Your 100 hertz component will be over here. So that is the 36 degree, and which corresponds to 100 hertz. Now, do you see any problem over here? Do you see any problem over here? When we are sampling at 1000 hertz for a 100 hertz component, okay, maximum frequency component, we are restricting our frequency component within the region of 0 to 36 degree. So if you have to design a low pass filter, you are left with only a very congested place to design the filter. Okay. So there is a cutoff. Okay, so there is a sweet point how you can design your digital filter. So if you go for the low cost data acquisition system, it will definitely help you in acquiring the data. But what it will do is that it will restrict your space to design the restrict your space in the Z plane to design your digital filter. Are you getting my point? Because you will be having a very congested area to place the poles and the zeros. Right? So, is there any way for that? Yes, there is a way. So, after you have sampled the data, so you are having per second 1000 data points. Okay. Then what you can do? What is the minimum requirement per second? What is the minimum requirement for the data point to be reconstructed faithfully? 100 hertz is your maximum thing, right? We discussed. What should be the minimum number of points in 1 second to faithfully reconstruct the signal? 1000 कैसे होगा? What is the Nyquist frequency? 200. So in 1 second, 200 points you should be having. Okay. So what you can do? 1 point means 1000 से you have to put it down to 200. Can we do it? Can we do it? We studied that. I talked about decimation, na? You cut every alternating point in the signals and systems. Didn't you do it? You do it. You did it, right? इसका मतलब you are not studying. So the thing is that over there, every alternative point we cut the points, right? So it was a decimation by 2. Here, what should be my decimation? By a factor of 5. By a factor of 5. So if you do it, you should be able to reduce the number of data points per second from 1000 to 200. So now, are you able to appreciate what you have studied previously? Why the decimation is required? Now, what is this basically? In a single digital system, you have acquired the data at a rate of 1000 frequency point, 1000 sampling frequency. But then again, you have resampled it and you have converted into 200. So same digital system, it is handling two types of sampling rates. So this kind of processing is called multi-rate DSP. Okay, MR. So when one digital system it is capable of handling two or multiple types of frequency sample frequencies, then it is regarded as multi-rate DSP. Okay. So it can be other way around also. In some cases, we might be interested in increasing the sampling rate. So in that case, it is called upsampling. And if we are reducing the number of data points, it is called the downsampling. So whether you are going for upsampling or whether you are going for downsampling, both the systems, it will be regarded as the multi-rate digital signal processing. Okay. So when you do the multi-rate DSP, while you are using this 1 kilohertz sampling frequency, what you are doing, you are fixing your sampling frequency over here at 1000 hertz, but artificially you are negating this and you are making it to 200 hertz. So my 100 hertz frequency, it is coming over here at minus 5. Am I right? So now you are having this 0 to 180-degree full range to design your filters. So it is increasing your scope to design the filters in a what do you call it, in a quite easily, basically. Okay, in a in a comfortable position. So you are in a comfortable position to design whatever type of filter you want to design, because you are getting a full range of this frequency axis in the range of 0 and pi. Okay, previously which was restricted to 0 and 36 degree. This we have already discussed, that when we are transforming from Laplace to Z domain, there is many to one mapping, because after 0 to pi, the same points are again repeating. So that is called many to one mapping. Now, using the same analogy, what we discussed in the Laplace domain, we can apply the same principle over here, but our frequency point, it has changed. My frequency axis is our unit circle. So our P point will be varying over here. So in that way, and all other principles, they remain the same. See, if you consider this point as the P, see D1, D2 we have calculated, theta 1, theta 2 we have calculated. Similarly over here. So the same analogy applies over here also, and see the same equation we are getting. Okay. Now comes the next part, how we can work with the examples. Okay. The thing is that suppose I am given with this transfer function hz equals to 1 by z minus 0.90 degree. So first I have to compute the location of the poles and the zeros. Okay, I have to compute the location of the poles and the zeros. So there are no z terms over here. So there are no zeros for this system, and it is one of the most simplest filter, one pole filter. Okay. So in the this denominator we are having z minus 0.9 phase angle. Okay. So this is the polar representation. The rectangular representation also we may I may put the equation. Okay. So I hope every one of you know how to come from the polar to the rectangular representation and vice versa. Okay. So over here, for the sake of understanding, I have given it in the polar representation form. So 0.9 and phase angle of 0. Okay. So what is happening? So at 0 angle, this is our 0 angle. Okay. We are on the real axis on the positive half. At radius 0.9, I have put the. Now I will ask you, find out the location of this amplitude response of this filter. Okay. So this is your real Z, the real Z, and this is your imaginary Z. I have not put the axis, but please be reminded while you are putting up your answers in the exam sheet, you have to put the axis. Okay? This is imaginary Z. In Laplace domain, it is sigma and j omega. In Z plane, it is real Z and imaginary Z, and then you are having the unit circle. Okay. Many students they do mistake when they come for the comprehensive viva while after the 2 years just before exiting. So if I ask what is the characteristics of the Z plane, they will just draw this X, Y, and Z. So please do not do this mistake. This is the basics. Okay. Your Z plane is this plane. We are out of time. So maybe we'll be discussing this in the next class because it will take some time.